Something is moving that you cannot see. Somewhere between being awake and not, the ceiling stops being a ceiling. It becomes a surface, a fact, something your eyes are resting against without much investment. The room is doing what rooms do at this hour, holding still, holding dark, holding the particular quality of silence that only arrives when everything that was supposed to happen today has already happened. Your body has made its decision. Your mind is still negotiating. And somewhere above all of this, above the roof, above the city or the field or whatever is outside, the stars are doing something you have probably never fully stopped to ask about. They are twinkling right now. Whether there are clouds or not, whether you can see them or not, the light is arriving. It has been travelling toward this planet for years, for centuries in some cases, moving at the only speed it knows how to move at, crossing this distance between where it started and where you are in a silence so complete that the word silence doesn't really cover it. And then, in the last fraction of a second of that entire journey, something happens to it. Something changes. The light enters the atmosphere, the thin, restless, breathing layer of gas that the Earth keeps wrapped around itself, and the atmosphere is not still. It is never still. Not at this hour, not on the calmest night you have ever stood outside in. Somewhere above you, warm air is rising from a road that absorbed heat for 8 hours and is still releasing it. Cold air is sliding underneath. Pockets of moisture are drifting east. The atmosphere is a body of weather in constant, quiet, purposeless motion, and it has been this way since before there were eyes to look up through it. The twinkling is not coming from the stars. That is the thing. The thing that, once you hear it, rearranges the whole picture. The stars themselves are not flickering. They are not sending a signal. They are not doing anything with their light except producing it, burning at temperatures that numbers cannot make you feel, throwing light outward in every direction, indifferent to where it goes or what it passes through. The light leaves, it travels, it arrives, and the arriving is where everything goes strange. Because arriving means passing through the atmosphere, and the atmosphere bends it. Not dramatically, not in a way you could watch happening, the way you could watch water bend a stick at the waterline. The bending is tiny. The atmosphere's refractive index, a measure of how much it slows light compared to a vacuum, differs from air parcel to air parcel by amounts that would need 9 decimal places to express. A pocket of warm air rising from a parking lot bends the light by an angle smaller than anything you could detect with your hands, your eyes, your ordinary instruments of experience. But there are thousands of those pockets, tens of thousands, stacked through the whole column of atmosphere between you and the star, each one slightly different in temperature, slightly different in density, slightly different in how much it bends the light, each one nudging the beam by a fraction of a fraction, and those fractions accumulate. By the time the light reaches your eye, it has been steered, gently, continuously, differently from moment to moment, and the steering makes it dance. Your eye reads the dancing as brightness. When the refracted paths happen to converge toward you, the star looks brighter. When they diverge, it dims. When the warm pocket drifts east and a cold one slides in, the geometry changes and the whole pattern shifts in milliseconds. The star pulses, it dims, it brightens. Sometimes, on turbulent nights near the horizon, it shifts colour, red, white, then something faintly blue, because different wavelengths of light bend by slightly different amounts, and the atmosphere is sorting them without meaning to. All of this is happening above you. Right now, if you went outside and lay on your back in the dark and let your eyes adjust, really adjust, which takes longer than people think, 20 minutes at minimum before the rod's fully open, you would see it, not as physics, as light that seems to breathe, as stars that look like they're aware of being watched, though they are not. As a sky that feels alive in a way that the daytime sky, washed out by the sun, never quite manages to. The atmosphere between you and the stars is maybe 100 kilometers deep. The journey the light made to get here was, for some of those stars, hundreds of light years long. And the twinkling, the thing you've probably noticed since you were old enough to notice things, the thing that got put into a nursery rhyme that has been sung to children for over 2 centuries without ever quite answering its own question, happens entirely in that last 100 kilometers, in the last fraction of a second, in the air that is right now, sitting above wherever you are. It is not the stars that are restless. It is the air between you and them, which has nothing in particular to be restless about, and goes on being restless anyway. The bending. Take a glass of water and put a pencil in it. You know what happens. The pencil appears to break at the waterline. The part submerged points in a slightly different direction than the part that isn't. The pencil is not broken. You know this. But your eye is reporting something true. The light coming from the underwater portion of the pencil is arriving at your eye from a different angle than it started. The water bent it, and so the pencil looks displaced, kinked, wrong. This is refraction, and it is so ordinary, so embedded in daily experience that it hides. It hides in the shimmering above a hot road on a summer afternoon. That's cold air and warm air sitting on top of each other, each with a slightly different density. The light from the sky bending toward your eye and making the road look wet. It hides in the fat bottom edge of a rainbow, which is not a trick of light so much as a demonstration of it. Blue bending more than red. The colours sorting themselves by how much each wavelength responds to the change in medium. It hides in the slight flattening of the sun at the horizon, its disk squashed by the differential refraction of the thick atmospheric column it's being viewed through. Everywhere. Constant. Invisible. Light bends when it moves from one medium into another that has a different index of refraction. That phrase, index of refraction, is measuring something specific. How fast light moves through the medium compared to how fast it moves through a vacuum. In a vacuum, light moves at approximately 299,792 kilometers per second, which is its maximum. In air at sea level, it moves slightly slower, not by much, about 0.03%, but that small reduction is enough. That small reduction is the difference between straight and bent. The bending happens at the boundary. When a light wave crosses from one medium into another, different parts of the wavefront hit the boundary at different moments, and the parts that have crossed slow down, while the parts that haven't crossed are still moving at the original speed. This difference in speed across the wavefront causes the whole wavefront to pivot. The wave changes direction. The angle of that change is described by Snell's law, which is a relationship between the angles and the refractive indices, and it is exact, and it has been tested so many times in so many ways that its reliability is not a subject of discussion among physicists. It just works. In glass, the refractive index is around 1.5. In water, around 1.33. In air, it is so close to 1.0, meaning so close to a vacuum, that the bending seems almost theoretical. But air is not uniform. This is the part that matters for what we're building toward, though we're not going to rush it. Air has temperature, and temperature changes the density of air, because warmer air has molecules moving faster and spreading slightly farther apart, reducing the number of molecules per unit volume, which reduces the refractive index. The difference is tiny. For a temperature change of 1 degree Celsius, the refractive index of air changes by about 0.00000009, a number that is difficult to take seriously, except that the atmosphere is not 1 degree different from itself. The troposphere, the lowest 10 to 15 kilometers of the atmosphere, where almost all weather happens, can vary by 30, 40, 50 degrees across small distances, especially at night when the ground cools rapidly and the air above it stratifies into layers that can differ significantly in temperature within just a few hundred meters. And the light from a star passes through all of those layers, thousands of them, each one bending the light by a tiny, almost nothing amount, and those tiny amounts add up. There is a city in the American Southwest, no particular city, but the kind of place where the air at night falls fast from the mountains and pools in the valleys, cold and dense, where on certain clear nights in winter the stars near the horizon shudder so violently that they seem to be on fire. Not twinkling, something more active than that. The red stars go red and then white, and then something greenish blue and back to red, cycling at a rate faster than you can follow. The physics involved is the same physics as the pencil in the glass. The angles are just more. What's happening is that the light from those low stars is passing through an enormous column of atmosphere, far more air than the light from stars directly overhead, because when you look toward the horizon, you're looking through the atmosphere at an angle, through its full thickness rather than just its depth. The column of air can be 10 or 20 times as thick as it is for stars near the zenith, and that column contains 10 or 20 times as many boundaries, 10 or 20 times as many chances for the light to be nudged. The bending is not one event, it is a continuous process. The light arrives at the atmosphere's top edge and immediately begins being steered, gently at first, at altitude, where the air is thin and the temperature differences between parcels are small. Then more actively as it descends into the denser, more turbulent lower atmosphere, each layer with its own temperature, its own density, its own refractive index, each one a slightly different prism. In the end, what we call the star's position in the sky is already a fiction. The true direction of a star, the geometric line from your eye to the star itself, is not where the star appears to be. Refraction lifts stars higher than they geometrically are. When a star appears to sit on the horizon, it is actually below the horizon. The atmosphere has bent its light over the edge of the earth and into your eye. You are seeing a star that has technically set. It's a minor displacement for stars well above the horizon, but it's there, and it's real, and it means that every star you've ever seen has been slightly elsewhere. The light is bent before it arrives, then it is bent again in the turbulence, Then it reaches your eye carrying a history of everything it passed through, and your eye collapses all of that history into a single point of light that seems to be sitting still in the sky, steady and ancient and confident. It is none of those things really, but it is beautiful in a way that knowing the physics only makes stranger, a portrait of nothing in particular. The atmosphere does not care what it is doing to the starlight. This is not a profound statement, it's just true. The air masses sliding over each other at the tropopause, the boundary between the troposphere and the stratosphere, sitting roughly 12 kilometers above sea level, are following pressure gradients and temperature differentials. They are not organized around any purpose. They are not moving in any particular direction because of any particular intention. A column of warm air rises from a field that absorbed heat during the day. It is still rising slowly at 10 o'clock at night. The air around it is cooler, and as the warm air ascends, it expands slightly, and a region of mildly different density forms at its edges, and the light from distant stars passes through that edge and bends. The warm column eventually loses its buoyancy. It spreads out. It mixes with the surrounding air and stops being a distinct thing. New temperature gradients form somewhere else. The pattern was never a pattern. On any given night, the atmosphere above a particular point on Earth contains dozens or hundreds of these convective cells, rising columns and sinking sheets and horizontal rivers of air moving at different speeds, like a fluid that has been heated unevenly and left to sort itself out. The technical name for this disordered flow is turbulence, and astronomers have a precise term for its effect on seeing: astronomical seeing. Good seeing means a night when the atmospheric turbulence above an observatory is calm, the temperature gradients are small, the cells are large and slow, and the starlight arrives with minimal distortion. Bad seeing means the opposite. The stars shudder, images blur. No telescope in the world can fix bad seeing from the ground. The best sites for optical telescopes on Earth, Mauna Kea in Hawaii, the Atacama Plateau in Chile, La Palma in the Canary Islands, are chosen partly for this. High altitude, so that the instrument sits above much of the turbulent lower troposphere. Stable airflow, ideally a steady laminar stream coming off the ocean, rather than air churned up by mountains or differential heating over land. Low humidity. The seeing at these sites, measured in arcseconds, where a smaller number is better, can reach 0.3 or 0.4 arcseconds on exceptional nights. At a typical mid-latitude site, it's more like 2 or 3 arcseconds. For comparison, the Hubble Space Telescope, operating above the atmosphere entirely, routinely achieves 0.05 arcseconds. The difference is the air. What's interesting, or strange, or both, is that the atmospheric turbulence responsible for poor astronomical seeing is often invisible to the naked eye. It is not the same as wind. You can stand outside on a perfectly still night, no breeze at all, and the stars overhead will be twinkling, because the turbulence is happening kilometers above you, at the tropopause or in sheets within the troposphere, completely disconnected from what the air is doing at ground level. The correlation between felt wind and observed twinkling is loose and unreliable. The turbulence is a property of the atmosphere taken as a whole. Its internal motions, its vertical structure, its response to differential heating and cooling across the Earth's surface. A lake cools differently from a city at night. A mountain forces air upward differently from a plain. All of it feeds into the turbulence profile of the atmosphere at any moment. The starlight reads that profile. Your eye reads the starlight. There is a scientist, a name that doesn't matter here, who once described the twinkling of a star as the most widely distributed atmospheric measurement device on Earth, free and available to anyone who happens to look up. You can infer the state of the atmosphere from the behavior of the starlight if you know how to read it. The faster the twinkling, the more quickly the turbulent cells are moving overhead, the more violent the colour shifts, the steeper the temperature gradients. The apparent motion of the star, the way it seems to jump slightly from one position to another, tells you something about the scale of the dominant turbulent structures. The star is not twinkling. The air is talking. Most nights nobody is listening in any systematic way. Why planets? Don't. Spend enough nights looking up and you notice it. The stars twinkle. The planets most of the time do not. Mars sits near the horizon on a turbulent autumn night, steady and orange, while the stars around it quiver and pulse and shift colour. Venus is worse, brighter, lower sometimes, and almost completely still. Jupiter barely moves. Saturn holds. Whatever the atmosphere is doing to the stars, it seems to leave the planets largely alone. This is not an illusion, and it is not because planets are somehow privileged or protected. The same turbulent air is between you and the planets, the same refraction, the same thousands of tiny boundaries, each one nudging the light. The planets go through all of it, and yet they hold. The reason requires following a piece of geometry all the way to its end. A star from Earth is a point source of light, not because it is small. Stars are enormous, many of them far larger than our Sun, but because they are so far away that their angular size, the angle they subtend at your eye, is effectively zero. The closest star to Earth beyond the Sun, Proxima Centauri, has an angular diameter of roughly 0.001 arc-seconds as seen from here. The best telescopes and interferometers in the world can barely resolve it. To your eye and to virtually any optical instrument, a star is a point. It has no width. It occupies a single direction. This matters enormously. When the atmosphere bends the light from a point source, it bends that single point. The point moves. It dances around, tens of arc-seconds on a bad night, as the turbulent cells carry it this way and that. Your eye sees this as brightening and dimming, because when the point dances away from your pupil you receive less light, and when it dances toward you, you receive more. But because the source is a point, because all the light is coming from a single direction, the turbulence affects all of it the same way at any given moment. A planet is different. A planet has angular size. Jupiter, at opposition, subtends roughly 47 arc-seconds as seen from Earth. Mars, at its closest, is around 25. Even Venus, which is small but close, spans 10 to 60 arc-seconds depending on its position in its orbit. These are not large angles. You couldn't see the disk of Jupiter with your naked eye the way you'd see a coin across the room. But they are real, measurable, physically significant. What this means is that the light from a planet is not coming from a single point. It is coming from an extended surface. Light from the left edge of Jupiter's disk and light from the right edge of Jupiter's disk are arriving from slightly different directions, separated by those 47 arc-seconds. And here is where the geometry resolves everything. The turbulent cells in the atmosphere are much larger than 47 arcseconds, the structures that cause twinkling, the refractive index fluctuations, the shifting boundaries, operate on scales of centimeters to meters in physical size, which translates to angular scales, much larger than the few arcseconds that separate different parts of a planet's disk. These cells are large enough that they affect all parts of the planet's disk roughly equally, at roughly the same moment. When a turbulent cell bends the light from Jupiter, it bends all of Jupiter. The whole disk shifts slightly. The shifting is real, and if you look through a telescope on a bad night, you can see the planet wobbling. But because the whole disk moves together, the total brightness doesn't change. The light from the left edge and the right edge are being deflected by the same amount in the same direction. They still all land in your eye. The integrated brightness stays constant. For a star, different turbulent cells affect different rays from the same point in rapid succession, creating rapid brightness changes. For a planet, the angular size of the disk means that many different cells are affecting different parts of the disk simultaneously, and those effects average out. The statistical fluctuations cancel. The planet holds steady. This smoothing effect is called the extended source effect, or sometimes just the seeing disk averaging, and it is a beautiful thing once you trace it. The planet doesn't resist the atmosphere. It is large enough that the atmosphere's fluctuations average to nearly nothing across its face. The star has no face. It is only a direction, and that direction trembles. There is a precise threshold, an angular size below which a source twinkles and above which it holds, and it depends on the turbulence profile of the atmosphere on any given night. Under particularly bad seeing, even small planets might show a flicker. Under exceptional seeing, even some very close large stars, red giants with measurable angular diameter, might hold slightly steadier than distant ones. But in practice, for practical observation with the naked eye on a typical night, the rule holds cleanly. Points twinkle, disks hold. You've been watching atmospheric physics every time you've distinguished a star from a planet by its steadiness. The planets are not calmer, they are wider. The history of a distraction. For a long time the twinkling meant something. Not physically. Not in the sense that anyone was trying to understand why it happened at a mechanistic level. It meant something in the older sense. It was a sign, a surface, a thing that could be read if you knew the reading. Sailors watched the stars for colour shifts, and their interpretations were passed down as rules of thumb that mixed observation with something else. A star that twinkled red near the horizon before a voyage was interpreted differently in different maritime cultures, but rarely neutrally. The behaviour of the stars was an index of something, weather, fortune, intention, and that indexical reading was so deeply embedded in how the night sky was used that separating observation from interpretation would have seemed like a strange thing to attempt. Aristotle mentioned the twinkling. He attributed it to the weakness of our vision at great distances. The eye, he suggested, loses its grip on things that are far away, and the sight wavers, and this wavering is what we see when we look at stars. Planets don't twinkle, he noted correctly, and explained this by their proximity. Planets are closer, and the eye can hold them. His mechanism was wrong in almost every particular. His observation was right. This is a common shape in the history of science. The right question, the wrong answer, and centuries of incorrect confidence before the correct architecture can be built. The twinkling was noticed by everyone. It was explained by almost no one correctly until the physics was available to explain it. The correct understanding requires the wave theory of light, a reasonably complete account of atmospheric structure, and the mathematics of refractive indices. None of these existed in anything like usable form until the 17th century at the earliest, and even then the pieces took time to assemble. Newton understood dispersion, the separation of light into its component colours, and that understanding is directly relevant to the chromatic component of twinkling. But Newton thought light was made of particles, which complicated the wave-based account of refraction. The wave theory of light, developed through the work of Christian Huygens and later Thomas Young and Augustin Jean Fresnel, gave the correct framework for understanding how light bends at boundaries. The mechanism of atmospheric refraction was worked out gradually through the 18th and 19th centuries, as astronomers became increasingly frustrated with the limitations it imposed on their observations. The twinkling shifted during this period from a sign to a problem. This is its own kind of history, the history of how something moves from being legible to being in the way. Once telescopes existed, the atmosphere became an obstacle. The magnification that a telescope provided also magnified the dancing. A small telescope might show you a moderately blurry Jupiter. A large telescope, under bad seeing, would show you a vigorously blurry Jupiter, the image boiling, never settling. The 17th century astronomer Christian Huygens, the same Huygens, built a telescope 70 feet long in an attempt to achieve greater magnification while reducing certain optical aberrations, and discovered that the atmosphere imposed a limit that optics alone could not overcome. You could build a larger mirror and collect more light. You could not, from the ground, collect steadier light. The 19th century produced the science of astronomical seeing as a systematic practice. Observers began classifying nights by their seeing quality, trying to correlate it with weather patterns, atmospheric conditions, the height and character of the jet stream. The correlations were real but messy. Good seeing defied prediction in the detailed way that mattered. Meanwhile, the twinkling continued to mean things in popular culture that had nothing to do with atmospheric optics. The nursery rhyme dates to 1806 in its published form, though the melody is older, borrowed, and its opening question, which asks what the star is, and frames the twinkling as the mystery to be solved, accidentally got the mystery right. The rhyme doesn't answer the question. It sits with the wonder of it and goes to sleep, which is perhaps the appropriate response. Astronomers eventually solved the problem not by understanding it better, but by going around it, placing telescopes in space, or developing technologies to correct for the atmosphere in real time. The Hubble Space Telescope, launched in 1990, was partly motivated by the desire to escape the seeing limit entirely. From orbit, with no atmosphere between the mirror and the stars, the images are limited only by diffraction, the fundamental blurring imposed by the finite size of the mirror, and not by the atmosphere's endless shifting. But for anyone standing outside on a clear night, the twinkling is still there. It has been there longer than anyone was able to understand it. It will be there long after the understanding is forgotten. The light crosses light years of vacuum and then dances for the last 100 kilometers, because of the uneven temperature of the air above a field, a city, a highway, a lake. The journey was indifferent to that last part. Near the horizon, everything gets worse. Lift your eyes. Follow a star from the horizon upward toward the point directly overhead, the zenith, and watch what happens. Near the horizon, the star shudders. It shifts colour. Red bleeds toward the edge of the spectrum, then blue, then back. On bad nights, the motion is visible even without a telescope, the star jerking a fraction of a degree from one moment to the next. The colours can be dramatic enough that people have reported an unfamiliar star near the horizon as something unusual, something anomalous, something to wonder at. Halfway up the sky, the same star, if you've tracked it long enough, is calmer, steadier. The colour shifts are still there, but subtler. The motion is damped. At the zenith, the star holds. Not perfectly, never perfectly from the ground. But the difference between a star at 10 degrees of altitude and the same star at 80 degrees is large enough to be striking. The reason is geometric and it compounds. When you look straight up, you are looking through the atmosphere along its shortest path, roughly perpendicular to the Earth's surface. The light from a star overhead passes through the full vertical depth of the troposphere, which is roughly 10 to 15 kilometers, and exits. It encounters a certain number of turbulent cells, a certain number of refractive boundaries. That's the baseline. When you look toward the horizon, you are looking through the atmosphere at an angle, nearly parallel to the Earth's surface. The light from a low star has to travel not 10 kilometers through the atmosphere, but something closer to 40 or 60 or more, depending on the exact angle, before it reaches you. The path is longer because you are cutting across the atmosphere's depth rather than through it. This is described by a function called the air mass, a measure of how much atmosphere a given line of sight passes through relative to the zenith path. At the zenith, the air mass is 1. At 60 degrees from the zenith, it's 2. At 75 degrees from the zenith, 15 degrees above the horizon, it's nearly 4. Near the horizon, the air mass climbs rapidly toward values of 10, 15, 20, and the calculation becomes complicated by the curvature of the Earth. More air mass means more chances to be bent, more turbulent cells, more refractive boundaries, more of every effect that the atmosphere imposes on starlight. The twinkling near the horizon is not a different phenomenon from the twinkling overhead. It is the same phenomenon, amplified by the geometry of where you're looking. The chromatic dispersion near the horizon is amplified the same way. Each wavelength of light has a slightly different refractive index in air. Blue light bends more than red light, as it does in any dispersive medium. Over a short atmospheric path, this separation is small, and the star appears white or slightly coloured only in turbulent bursts. Over a long atmospheric path near the horizon, the cumulative dispersion is much greater, and the star's image is genuinely spread into a tiny spectrum. The blue image and the red image of the same star are separated enough that turbulence can, for a moment, flash them independently. This is why a low star seems to flash through colours. It's not changing colour so much as showing you its spectrum one wavelength at a time, as the turbulence redirects each colour differently. The phenomenon is most vivid just after sunset or just before sunrise, when a bright star or planet sits at or near the horizon, and the atmosphere is thermally active. The ground is either releasing the day's heat or beginning to warm, and the air near the surface is churning. There is also a related effect, less related to twinkling but worth sitting with, the green flash. Under conditions of exceptional atmospheric clarity and a very flat horizon, over an ocean usually, the last sliver of the setting sun can appear briefly green. This is the dispersed refraction of sunlight taken to its visible extreme. The red component of the sun's light is the last to disappear below the horizon, but it's also bent the least, so the red image sets first. The green image lingers a fraction of a second longer. The blue image should linger even longer, but it's scattered away by the atmosphere before it reaches you. What remains for a moment is green. The physics is the same physics. The geometry is the same geometry. The scale is different. Looking toward the horizon means looking through more of the same thing. The same thing accumulated becomes something else. What the telescope sees. Point a large telescope at a star and look. What you expect, if you haven't done this before, is to see a star, a point of light, maybe brighter, maybe more detailed, resolved perhaps into something that wasn't visible to the naked eye. What you see instead, on most nights from most locations, is a disk. Not a disk with features, not a disk you can study. A blurry, wandering, boiling blob of light that refuses to hold still. The star that looked like a crisp point to your naked eye has been smeared by the telescope into something that writhes. The magnification that was supposed to reveal detail has instead revealed turbulence. This is not a failure of the telescope. The telescope is doing exactly what it is supposed to do. It is collecting more light from a larger area, focusing that light, and magnifying the result. The problem is that the light it collected was already distorted before it arrived at the mirror. The technical term for this smeared disk is the seeing disk, and its angular diameter is used as the primary measure of atmospheric seeing quality. A seeing disk of 1 arc-second means the atmosphere is blurring the star into an apparent size of 1 arc-second. Under these conditions, two stars separated by less than 1 arc-second cannot be distinguished. A seeing disk of 3 arc-seconds means the conditions are poor and the resolution limit is correspondingly coarse. For comparison, the diffraction limit of a large telescope, the blurring imposed by the physical size of the mirror, the fundamental optical minimum, can be far smaller than an arc-second. A telescope with a mirror 1 meter across has a diffraction limit of about 0.12 arc-seconds at visible wavelengths. A 10-meter telescope has a limit of 0.012 arc-seconds. But if the seeing is 1 arc-second, neither telescope can do better than 1 arc-second, no matter how large the mirror is. The atmosphere has imposed its limit, and the mirror's quality is irrelevant until you get above it. The history of telescope building in the 20th century ran headlong into this wall. The mirrors got bigger, the detectors got more sensitive, the mechanical mounts got more precise, and the resolution stayed stuck at what the atmosphere allowed. You could collect 10 times as much light with a bigger mirror. You could not collect 10 times more information per photon. What you see when you look at a star through a large telescope during mediocre seeing is the atmosphere made visible. The boiling is real. The wandering is real. The seeing disk, traced over time, maps the distribution of turbulence in the column of air the telescope is looking through at that moment. Astronomers developed ways to measure this. specialized instruments called seeing monitors that image a reference star and measure the width of its disk continuously, tracking how seeing quality changes through the night, trying to predict when it would improve. There is something almost personal about watching bad seeing through an eyepiece. You become aware of the air. You become aware that you're not looking at space but at the bottom of a moving fluid, peering through it toward what lies above. Long exposure photographs average out some of the rapid turbulent motion, but cannot recover lost resolution. The result is a somewhat smoother disk, still blurred, the averaging of many slightly different positions. Short exposure photographs can sometimes freeze the turbulence, catching a moment when the seeing was briefly better, and a technique called lucky imaging exploits this by taking thousands of short exposures and selecting only the fraction of frames where the seeing happened to be good. It works, sometimes, for bright sources. It is not a solution. The real solution required a fundamentally different idea. But that comes later. For now, the telescope sees what the atmosphere allows it to see. And what the atmosphere allows it to see on most nights from most places is not the star. The star is behind all of this. Rubber mirrors. The idea when it arrived was to fight the atmosphere with itself, not to escape the atmosphere, not to wait for the atmosphere to be still, but to measure the distortion it was imposing on incoming light in real time fast enough to undo it, and to apply a correction to the telescope's optics that was exactly the opposite of what the atmosphere was doing. If the atmosphere was pushing the wavefront one way, push it back, continuously, faster than the atmosphere could change. This is adaptive optics, and it sounds, when described plainly, like an obvious idea. It also requires solving a set of problems that spent decades being unsolvable. The first problem is measurement. To correct for the atmospheric distortion, you need to measure it. To measure it, you need a reference, a source of light whose true shape you know, so you can compare what arrives at the telescope to what should have arrived. A star is the ideal reference. It's a point source. So the wavefront from a star should arrive flat, and any deviation from flat is the atmosphere's fault. But to correct the atmospheric distortion, you need a reference star close enough to the science target that the light passes through the same column of atmosphere. And that reference star needs to be bright enough that you can measure its distortion many times per second, because the atmosphere changes on timescales of 10 to 100 milliseconds, and your measurements and corrections need to keep up. Bright, nearby reference stars do not exist in all parts of the sky. This is a severe constraint. The solution to this problem, the one that made adaptive optics practical for most of the sky, involves creating a fake star with a laser. A powerful laser beam is aimed upward from the telescope and tuned to a wavelength that excites sodium atoms in the mesosphere, a layer of the upper atmosphere about 90 kilometers up, producing a glowing spot, a pinpoint of light in the sky. This artificial star, called a laser guide star, can be placed anywhere in the sky the telescope is looking, and can be made bright enough to measure the distortion at the required rate. The laser guide star has a limitation. Because it sits at finite altitude, the light from it travels through the atmosphere at a slightly different angle than light from a real star at effectively infinite distance. This means the laser guide star correctly samples most of the atmospheric turbulence, but not all of it. The turbulence very close to the top of the atmosphere is sampled at a slightly different part of the wavefront. In practice, this requires one or more natural guide stars to be used in addition to the laser to correct for this residual error. But the laser guide star solved the fundamental access problem. You can now, with a laser and a bright reference, apply adaptive optics to almost any target anywhere in the sky. The second problem is actuation. To correct the wavefront distortion, you need to deform the telescope's mirror, or a small additional mirror in the optical path, so that it counteracts the atmospheric aberration. The mirror needs to flex. It needs to flex in real time, at the rates required by the changing atmosphere, with the spatial resolution required by the scale of the turbulent structures, and with the precision required by the wavelengths involved. These mirrors exist. They are made of thin reflective material. In some designs, a monolithic sheet of glass or silicon just a few millimeters thick, supported by an array of tiny actuators, devices that can push and pull at specific points with very small displacements. There might be hundreds of actuators, or thousands, each one capable of moving its part of the mirror by fractions of a wavelength of light. The actuators receive commands from a control computer that has taken the wavefront sensor's measurement, calculated the required correction, and issued commands to each actuator, all within a few milliseconds. The whole system, wavefront sensor, control computer, deformable mirror, and all the optics that route the light through them, runs in a continuous loop. Measure, compute, correct, measure again, correct again, 50 times a second, or 100 times, or more, depending on the conditions. When it works, it is a strange thing to see. A star that was boiling in the seeing disk sharpens suddenly to something close to a true point. The atmosphere is still turbulent. The light is still being bent and rebent as it descends. But the mirror is warping to meet it, to undo what the air has done, and the result is light arriving at the detector in something closer to its true, undistorted state. The correction is never perfect. There are turbulent structures too fine for the actuators to resolve, and turbulence too fast for the loop to track, and residual errors in the wavefront sensing. But the improvement is dramatic. A telescope operating with adaptive optics can approach its diffraction limit, the resolution imposed by physics rather than the atmosphere, at least in the infrared, and increasingly in the visible range as the technology improves. The mirrors flex, the stars hold still. The atmosphere is still there, still churning, still bending everything that passes through it. But for a few seconds at a time, in a narrow patch of sky, the correction keeps up. Scintillation. The word itself is from Latin. Scintilla, a spark. Scintillation is the technical name for the twinkling of stars, and for a related set of phenomena that appear whenever a signal passes through a turbulent medium. Radio signals from pulsars scintillate as they pass through the interstellar medium. GPS signals scintillate as they pass through the ionosphere. The physics is the same physics, scaled to different media, different wavelengths, different turbulent structures. But we're staying with the stars. Stellar scintillation, measured carefully, is not one thing. It is at least 3 distinct phenomena layered over each other, each produced by a different aspect of what the atmosphere is doing to the light, each measurable independently with the right instruments. The first is intensity scintillation, the rapid variation in the apparent brightness of the star. This is what the naked eye reads most easily. The star brightens and dims, sometimes quickly enough that individual pulses are hard to follow, sometimes slowly enough that each brightening seems distinct. The time scale of intensity scintillation depends on the speed at which turbulent cells are moving across the line of sight. Faster winds aloft mean faster fluctuations. The amplitude depends on the strength of the turbulence, a quantity called the refractive index structure parameter, written c sub n squared, which summarizes how much the refractive index varies within a given volume of air. High c sub n squared means strong turbulence, large scintillation. Low c sub n squared means calm air, steady stars. The second is chromatic scintillation. The colour shifts. Because air is a dispersive medium, because different wavelengths of light have slightly different refractive indices, the path that blue light takes through the atmosphere is not exactly the same as the path red light takes. The turbulent cells bend blue differently from red. When a turbulent cell shifts the blue image of the star away from your eye, while the red image happens to be redirected toward you, the star appears reddish. A fraction of a second later, the geometry reverses, or a different cell dominates, and the star goes blue. The colour oscillates. The amplitude of chromatic scintillation depends on how dispersive the atmosphere is for a given set of wavelengths, which is to say, on the difference in refractive index between the wavelengths you're comparing. This difference is larger between blue and red than between, say, two nearby shades of green. Stars with strong chromatic scintillation near the horizon look like they're on fire. Red, white, blue, red, cycling faster than the eye can follow cleanly, the colours bleeding and shifting in a way that is unmistakably atmospheric and has nothing to do with what the star is doing. The third is positional scintillation, the apparent motion of the star. The star seems to jump. Under severe seeing, the jumps can be visible to the naked eye, particularly near the horizon. Through a telescope, the star traces a small erratic path across the field of view, never settling, the pattern of motion changing as new turbulent cells drift across the line of sight. The scale of positional scintillation is related to the scale of the dominant turbulent structures. Large cells produce slow, large amplitude wanders. Small cells produce rapid, small amplitude jitter. In practice, all three types of scintillation are happening simultaneously, overlapping, mixing. The brightness varies, the colour shifts, the position wanders. Your eye integrates all of this into the impression of a twinkling star, which is a perceptual averaging of three separate physical processes. The mathematical framework for describing atmospheric turbulence, including scintillation, was developed in the 1940s and 1950s by the Soviet mathematician Andrei Kolmogorov. Kolmogorov's turbulence theory describes how energy is distributed across different scales in a turbulent fluid, how the large-scale energy of, say, a convective column kilometers across cascades down through successively smaller eddies until it reaches scales small enough that viscosity dissipates it as heat. The distribution of energy across scales follows a power law that Kolmogorov derived from dimensional analysis and physical reasoning, and it has been measured in the atmosphere and found to hold remarkably well across many orders of magnitude. This Kolmogorov turbulence spectrum is the foundation for almost all quantitative work on astronomical seeing. From it, one can derive how the wavefront from a distant star is distorted as a function of scale, and how a telescope of a given diameter will be affected. The characteristic scale at which the wavefront is significantly distorted, called the Fried parameter after David Fried, who derived it in 1966, tells you the effective resolution limit of any telescope under given seeing conditions. If the Fried parameter is 10 centimeters, no telescope larger than 10 centimeters will see a sharper star than a 10 centimeter telescope, because all that extra aperture is collecting light whose wavefront is already distorted at scales smaller than the aperture. On an excellent night at a world-class site, the Fried parameter might reach 50 or 60 centimeters. On a typical mid-latitude night, it might be 5 to 10 centimeters, about the diameter of a large coffee can. The turbulence is structured. The scintillation is structured. It only looks random. There is a measurement technique called scintillation detection and ranging, CIDAR, that uses the scintillation pattern to reconstruct the vertical profile of turbulence in the atmosphere. Two stars close together in the sky are observed simultaneously, and the way their scintillation patterns correlate with each other, or don't, as a function of time reveals at what altitude the turbulence is strongest. The atmosphere, read through its effect on starlight, becomes legible. The star twinkles, the instrument listens, the atmosphere confesses. The same light left, anyway. The light didn't know. This is the starting point, and it keeps being the starting point no matter how many times you approach it from a different direction. The light that is arriving at your eye right now, or that would be arriving if you were outside, if the clouds had cooperated, if you had thought to look up, left its source without any knowledge of what it would pass through. It left without intention. It left the way heat leaves a surface. Because that is what it does, because the physics of the situation gave it no other option. A star burns, and burning produces photons, and photons travel outward in every direction simultaneously. And some of those photons happen to be aimed at a small rocky planet orbiting an unremarkable star in an outer arm of a middling galaxy. And they go. They have always been going. They were going before the planet had oceans. They were going before the planet existed at all. And for almost the entire journey, nothing touched them. This is the part that resists being felt even when it is understood. The distances involved are not large in the way that a mountain is large, or a continent, or an ocean. They are large in a way that comparison cannot reach. When you say that the light from Betelgeuse, the red supergiant that sits at the left shoulder of Orion, visible on winter nights from most of the inhabited world, has been travelling for somewhere between 500 and 700 light years, the number is technically meaningful and experientially empty. 500 light years means that the light now arriving at Earth left Betelgeuse at a moment when there was no printing press, no telescope, no systematic astronomy in the European tradition, no one anywhere on Earth who had any idea what a light year was, or that such a concept would eventually be needed. The light was already on its way before Gutenberg. It arrived, is arriving, now. Whatever now means to you at this particular hour. During all of that time, 5 centuries of travel, give or take. The light moved through a medium that offered it almost nothing. Interstellar space is not completely empty. There is gas, thin, mostly hydrogen, dispersed so finely that a cubic meter of it might contain fewer atoms than the best vacuum a laboratory can produce on Earth. There is dust, particles of carbon and silicate, the remnants of old stellar explosions, distributed so sparsely that light can travel thousands of light years before encountering enough of it to matter. There are magnetic fields and cosmic rays, and the faint background radiation left over from the early universe, and none of it significantly alters the journey of a photon moving from one star toward another. For practical purposes, for the purposes of what we're talking about, the photon travels in a straight line at the speed of light for its entire journey, undisturbed. The wavefront that arrives at Earth is flat, or very nearly flat. Technically, it is a sphere expanding outward from the source, but a sphere of radius 500 light-years is so enormous that any portion of it small enough to fit inside the Earth's orbit is indistinguishable from a flat plane. Flat means ordered. Flat means all the peaks and troughs of the light wave are perfectly aligned, the way water waves are flat and orderly when they begin far out at sea before anything disturbs them. The wavefront has crossed half a millennium of space and arrived in perfect shape, carrying the same information it had when it left. And then it enters the atmosphere. The top of the atmosphere, the boundary where space ends and the thin upper air begins, is not a sharp line. It is a gradient. The air gets denser as you descend, slowly at first, then more rapidly. The thermosphere, where satellites in low Earth orbit operate, has air so thin that a spacecraft moving through it barely notices. Then the mesosphere. Then the stratosphere, where the ozone layer sits and where the air is cold and relatively stable. Then the tropopause, the boundary layer between the stratosphere and the troposphere, at roughly 10 to 15 kilometers altitude depending on latitude and season. And then the troposphere itself, the lowest and densest and most chaotic layer, where all weather happens, where clouds form and storms develop, and the temperature and humidity and density vary enormously from place to place and moment to moment. It is the troposphere that does most of the work. The light enters the top of the atmosphere and immediately begins to be affected, gently, almost imperceptibly at first, by the thin air of the upper layers. As it descends into denser air, the effects compound. Each layer has a slightly different temperature from the layer adjacent to it, and temperature differences produce density differences, and density differences produce differences in refractive index, that number expressing how much a medium slows light compared to a vacuum. And wherever the refractive index changes, the light bends. The wavefront, which arrived flat, begins to be deformed. Different parts of it encounter different air at different moments, and those parts bend differently, and the flat plane begins to develop ripples, wrinkles, distortions that grow more complex as the light descends. By the time it reaches your eye, the wavefront is not flat anymore. It is a crumpled, irregular surface, different from the wavefront of any other star, different from what it was a millisecond ago, different from what it will be a millisecond from now, because the air it passed through a millisecond ago has already moved, already mixed, already become something slightly different. The wavefront is a record of everything the light passed through on its way down, a fingerprint of the atmosphere at the precise moment of arrival. Your eye doesn't know how to read that fingerprint. What your eye reports is brightness, the integrated intensity of whatever light arrives at your pupil. When the crumpled wavefront happens to focus slightly toward you, more light lands on your retina, and the star looks brighter. When it defocuses, the star looks dimmer. The changes happen many times per second, too fast to follow individually, fast enough that your visual system averages them into a general impression of instability, of movement, of something that is not quite still. You see a star that breathes, that pulses, that seems on some level alive. It is not alive. The star is not doing any of this. The star at this moment is doing what it has been doing for millions or billions of years, fusing hydrogen into helium in its core, generating the pressure that holds it against its own gravity, converting a small fraction of its mass into energy every second in quantities that dwarf anything a human civilization has ever produced. The star is a thermonuclear process on a scale that makes the word thermonuclear sound small. It has no awareness of the photons leaving its surface. It has no awareness of anything. It is a ball of plasma, and it burns, and the light leaves. That is the full extent of the star's involvement in the twinkling. Everything else, the wavefront distortion, the brightness fluctuations, the colour shifts, the apparent positional jitter, belongs to the atmosphere, specifically to the column of atmosphere above wherever you are at this moment, which is different from the column of atmosphere above a point 100 meters to your left, which is different again from the column above the next town, the next mountain range, the next ocean. The atmosphere is not uniform. It is never uniform. It is a body of uneven, locally variable air, and the light from each star passes through its own particular column of that air, and no two columns are the same, and no column is the same from one second to the next. This is why the twinkling looks different depending on where you are. At sea level on a humid summer night, with warm air rising from the ground and mixing with cooler air descending from above, the twinkling is active, rapid, chromatic. The stars near the horizon shuddering and colour cycling in a way that can be startling if you're paying close attention. In the mountains, where you're already above some of the atmospheric turbulence and the air is thinner and drier, the stars hold steadier. At the summit of Mauna Kea in Hawaii, at 4,000 meters, above roughly 40% of the Earth's atmosphere, the stars barely twinkle at all by the standards of sea level. From orbit, from the International Space Station, from the Hubble Space Telescope, from any platform above the atmosphere entirely, stars do not twinkle. They are fixed, steady points of light. They have always been fixed, steady points of light. The twinkling was never theirs. It was always ours. And there is something worth sitting within that. Not a conclusion exactly, more like a texture to the idea. The thing that has seemed most alive in the night sky, the breathing, pulsing, colour-shifting quality of starlight that has been noticed by every culture that ever looked up, that got embedded in nursery rhymes and navigation guides and poetry written by people who had no idea what was causing it, is a property of the air, our air, the atmosphere that we breathe, that carries weather, that turns red at sunset for the same dispersive reasons that it turns stars red near the horizon. The beauty is local. The beauty is an accident of the medium. The beauty has nothing to do with the source, and yet the source had to be there. The light had to make the journey. 100 kilometers of turbulent air cannot twinkle on its own. It needs something to twinkle. It needs 5 centuries of photons arriving from a dying star, flat and ordered and unaware, to give the atmosphere something to work with. The twinkling is a collaboration between something very far away and something very close, between a nuclear process that has been running since before complex life existed on Earth, and a pocket of warm air that rose from a parking lot 3 hours ago and will mix back into the general atmospheric circulation by morning. The star contributed the light. The atmosphere contributed the dance. You contributed the eye that noticed. There is a version of this that wants to resolve into something, a lesson, a takeaway, a reason why understanding the physics makes the experience better or worse or different in some clean way. But the honest version is messier than that. Knowing that the twinkling is atmospheric does not make the stars look steadier. They still pulse. The red ones still shift toward blue on turbulent nights. The blue ones still flare and dim in ways that feel intentional, even knowing they are not. The knowledge sits alongside the experience without replacing it. You can hold both things. The physics, which is exact and verifiable, and has been tested in every way that physics gets tested, and the experience, which is whatever it is when you're lying on your back at this hour with the ceiling trading places with the ski in your half-asleep mind. The light crossed whatever distance it crossed. Let's say it was hundreds of years for the closer ones, thousands for the ones that look the same to your naked eye but are not remotely. And it crossed that distance through a vacuum that had no opinion about it, and it arrived at the top of the atmosphere in the same shape it left, flat and ordered and carrying all of its original information. And then the atmosphere took a few hundred milliseconds to turn it into something that looks ancient and breathing and somehow personal, the way things that happen slowly over very long distances can feel personal when they finally arrive. The light left before you were born, before your parents were born, in some cases before any human alive today was born. It was aimed at a point in space that would eventually be occupied by a planet that would eventually develop an atmosphere that would eventually be breathed by a species that would eventually learn to look up and wonder what was causing the brightness to fluctuate. It didn't know any of that. It just went. And the atmosphere, which doesn't know anything either, which is just air following pressure gradients and temperature differentials in the mindless way that air does, received it and scattered it and bent it and sent it to your eye in a form that feels like the sky is doing something for you specifically, something intended, something that has travelled a long way to reach you. It has travelled a long way to reach you. The intention part, though, that part belongs to the air, which has none, and to you, which is the only place in this whole arrangement where anything like noticing is happening at all. The star doesn't notice. The atmosphere doesn't notice. The light arrives, the air bends it, the eye receives it, and somewhere in that final step, the step that happens not in space, not in the upper troposphere, but in the few centimeters between the surface of your eye and the part of your brain that says, something is moving up there. The twinkling becomes real, becomes the thing it is, becomes whatever it is you see when you look up at a clear night and feel, briefly, that the universe is awake. The universe is not awake, but you are, or almost, or somewhere in between, which might be exactly the right state for looking at stars that have been travelling since before you existed toward an atmosphere that has been waiting for nothing in particular and arriving quietly, as they always have. The twinkling goes on. The air above you shifts. The next parcel moves in. The wavefront deforms slightly differently than it did a second ago, and the star that held for a moment shudders again. It doesn't know, neither does the air. Only you know, and you are almost asleep, and the knowing and the not knowing are becoming harder to tell apart.